today. So what we're going to do first is we're just going to be reviewing the acid, base, and buffer notes, the old acid, base, buffer notes from Unit 2. Then once we're done with that, we're going to go to our new acid, base notes, and then we'll take a look at buffers, we'll take a look at titrations. That's really all that's left, okay? So let me just do a quick little skim or scan of what we've already done. Okay, so we've already done, we know that acids, neutral, bases, don't forget, pen here, that it goes in order, that it goes acid, and then 7, and then base. When I say in order, A comes before B in the alphabet. So if you're before number 7, then that's going to be acidic, and then anything over 7 would be considered basic. Okay. So if we scroll down here, we can see different examples of acids and bases. I always like to say H to the acid, OH to the base. Always keep your goggles on, safety for the face. So if it starts with an H, it's an acid. If it ends with an OH, it's a base. Now, there are different definitions of acids and bases, but the one that we always use, the basic one that we always use, is called the Arrhenius definition, okay? And Arrhenius is that H, if it starts with an H, it's an acid. If it ends with an OH, it's a base. Bronsted-Lowry, does anybody remember what Bronsted-Lowry says about an acid? It's very, very similar to this. You can just say it.
It increases the H+ ion.
Good. So if something releases hydrogen ions, or they'll call them protons, into a solution, that's called an acid, okay? So then bases definitions are a little bit different in the Bronsted-Lowry. Bases do what? They accept the protons, okay? So different from Arrhenius's definition that says it ends in an OH, okay? So just keeping that in mind. How do we name acids? So remember, it's like the hide, itis, and the adic. So if you look at a periodic table, and we have anything that does not have, that's not a polyatomic ion, is going to start with hydro. So for example, if I point to nitrogen, that would be called, H3N would be called hydronitric acid. What if H2O is just water, right? So that doesn't count. What about HF? Hydrofluoric acid. HCl. Hydrochloric acid. HBr. Hydrobromic acid. H3P. Hydrophosphoric acid. H2S. Hydrosulfuric acid. Okay, so if it starts with hydro, there's only one polyatomic ion that we were doing. It was HCN. That, because it ends in ide, it's cyanide. That one would also be hydrocyanic acid, okay? But the rest of the polyatomic ions either end in ite or ate, okay? And if it ends in ite, then you're going to change your ending to, do you remember, hide, ite, us in the ate-ic, okay, in the attic. So, or people have different ways of doing that, but if it ended in ite, you're going to make it ic. So sulfite would be sulfurous acid, and if it ends in ate, you're going to change it to an ic, so that would be sulfuric acid. Okay, so just making sure that you know how to name those. Okay, and then we had some examples. Okay, so water is going to self-ionize, okay? And so when it ionizes, it's going to break up into what? We say H plus and OH minus, but it's not really H plus. It's called the hydronium ion, which is H3O plus. Very good, okay? So the hydronium ion, but we do call it H plus. There are all these disclaimers about it. And so when we have an equation like this, water is a liquid, okay? And what we can do is we can come up with a K, an equilibrium expression for it. So I believe it happens on the next page. Let's see. Yes, perfect. KW. What is K equal to, everybody? K is simply equal to concentration of products over reactants. What's true about the reactant in this case, though? It's a liquid, so we don't include it. So what's the KW? It's simply called the ion product constant for water, okay? So it's the equilibrium constant for water. So K is simply equal to the concentration of H plus times OH minus. Or, instead of H plus, what would we use? What should we be using, really? H3O plus times OH minus. And that equals 1 times 10 to the negative 14. Really nice, because if you know the H plus concentration, you can always find the OH minus concentration. There's only one other variable then. You would call that X. So if I know my OH minus, is 1 times 10 to the negative 7, what should my H plus be? 1 times 10 to the negative 7. If my OH minus is 1 times 10 to the negative 10, my H plus should be 1 times 10 to the negative 4. Okay? So if it's a multiple choice problem, they give you one and you can figure out the other one. Sometimes the answers are far enough apart that you can basically estimate it, okay, to figure out what the other one is. Because again, no calculator, right, if it's multiple choice. Okay, and then again, be careful. If they give you the OH minus, I always like to switch it to H plus before I figure out if it's an acid or a base. So for example, in this case, if I've got my OH minus at 10 to the negative 12, my H plus should be around what? 10 to the negative 2, right? And if my H plus is 10 to the negative 2, my pH is going to be around what? Around 2. And so if your pH is around 2, would you call that an acid or a base? An acid. Okay. So I always like to switch it to think about my H plus. So if they give you OH minus, always be careful, because when you negative log, or you can just negative log it if you're able to use a calculator, you negative log that, obviously you're going to get something around 12, right? And that's your hydroxide concentration. If your hydroxide concentration is really small, though, you can expect it to be acidic, okay? So just keeping that in mind. All right. There was a time where we were talking about, okay, if I gave you the substance, for example, in this case here, I know my OH minus concentration. I can figure out my H plus concentration. I can say it's an acid, okay? But if I told you that my sodium hydroxide concentration was equal to 3 times 10 to the negative 12, what would you say the pH was approximately? pH is about what? It's about 2, okay? Would that make sense that I put sodium hydroxide, I have a solution of sodium hydroxide, and the pH is about 2? It doesn't make any sense, does it? Because what do we expect the pH of a base to be? Above 7. So why am I getting a pH of 2? Because there's barely any what in the water? There's barely anything in it, okay? There's barely any sodium hydroxide in it. 3 times 10 to the negative 12 molar? That's such a small amount. So I would say my pH is not 2. What would my pH be equal to? 7, okay? So then we would say it's neutral. We would say it's pretty much just water, okay? But if I actually give you, if I say hydroxide is equal to or hydrogen is equal to, that's a different story from me actually giving you a substance, okay? So that was kind of a confusing part when we did this back in Unit 2. All right. Okay, so let's take a look at the equations. There are 4 major equations. Really easy, but really, I would say it's kind of like, I don't know, 3 maybe major equations. So the first one is, what is the definition of pH? So pH is simply the negative log of H plus, and so then POH is the negative log of OH minus. So pretty easy just by definition. So if you're ever given the H plus and you want to know the pH, or you're given the OH minus and you want to know the POH, you literally just plug it right into your calculator. Negative, find your log button, type your concentration in, hit enter, okay? Remember, where this gets confusing is, what if I told you, so go ahead and try this in your calculator right now, what if I told you that my pH was equal to 3.72 and I wanted to know what my H plus was equal to? So go ahead and calculate this and let's see what you get. Okay, so are you getting something like 1.905 times 10 to the negative 4? Now, if you're getting an error, you did it wrong in your calculator, okay? How did you get that? So the H plus should be equal to something like and I'm going to do 2 sig figs, by the way, because you only look after the decimal for your sig figs. So I'm going to do 1.9 times 10. I'm just going to write this just to kind of make this easier here. And then this would be in molarity. Okay. pH doesn't have a unit, but H plus obviously has a unit of molarity. Okay. Only the numbers after the decimal count. If you didn't get this answer, you probably plugged it in wrong. What do you have to do to plug this in? 10 to the negative of the number. So what you should have in your calculator, now on mine, I have to hit Shift Log to get the 10 to the X button. So I'm going to do 10, and then it's to the, I need the negative because for the equation, you're going to move the negative over to the other side. Okay, so the negative has to go over to the other side, and then that would be negative 3.72. And so once you plug that into your calculator, you should get that answer. Okay. All right. Any questions so far? Questions so far? Okay. Let's scroll down a little bit. We already said about how to figure out pH, H+. Okay, let's go to the other two equations. Okay. The other equation, really easy. If you know the pH, you can always figure out the pOH. If my pH is 8, my pOH is 8, my pH should be 6. Perfect. So just subtract to figure the other one out. Now in this case, we've got H plus and OH minus. It's exactly the same equation as this, but in this case here, we're using like the negative log, and so that's why we're adding these two together. But in this case, we're going to use the correct number, which is 1 times 10 to the negative 14. This is our KW equation. So this is equal to our KW. That is the KW equation. If I know one, I can figure out the other. But now I'm not adding and subtracting. What am I doing? Multiplying and dividing. Well, dividing, right? Because you're always going to do this one divided by that, or this one divided by that to figure out the other one. Okay. Pretty easy. Trying to see if there's anything. We already talked about that 7 situation. So if they give you the name of it, and they tell you it's an acid, and it's HCl, but you get the pH of 12, that doesn't make any sense. A pH of 12 should be a base. So that makes no sense, and so you would just make your pH 7 instead. Okay, let's take a look at the next page. These are just the equations that are going to be given to you. A lot of the acid-base ones are actually under equilibrium, so like the Ka, the Kb, we're going to come back to what is Kw equal to, and it's actually also equal to Ka times Kb. So where Ka, so if you have the weak acid, your weak acid and your weak base are going to be interrelated. So we'll come back to that. And then we'll go through some of these equations later on too. There's this one is called the Henderson-Hasselbalch. It's one of my favorite equations. So we'll come back to that. And then the other ones are really just definitions. Okay. So then we got into how do you calculate molarity versus how do you calculate pH? Pretty easy. We already know molarity. It's moles over liters. Don't forget, is it just liters of solvent or is it total liters? Total liters. Don't forget that. Okay, it's going to be liters of your entire solution. Okay, so if you want to know the molarity, switch your grams to moles and then divide by your liters. But if you want to know the pH, you need to do what to the molarity? Negative log it. Awesome. So once you negative log it, so once you find your H plus, you just negative log it. Now people will say, well, how am I supposed to figure out my H plus? They gave me HCl in water. Well, if you know your HCl concentration, what's my ratio of H plus to HCl? 1 to 1. So if you figure out that it's 0.0893, should really just put this in brackets. If you figure out it's oh, that's the mole still. If you figure out it is 0.0595 molar HCl, what's my hydrogen concentration then? 0.0595. It's going to be the same. Okay, so keeping that in mind. If it's a base, don't forget, you need to make sure that if they ask for the pH, once you find, you negative log it. That's not pH, that's pOH. So then what do you do to find the pH? Subtract from 14. Awesome. Okay. So once you get to your pOH, which like I found there, then you have to do 14 minus your answer in order to get that. The other thing I wanted to remind you of, and it will be in the notes today, is if you have a 2 and it's a base, you do have to multiply the hydroxide concentration is multiplied by 2. So if you're looking and you're like, I figured out that my calcium hydroxide is a 0.453, what would I have to do to figure out my hydroxide concentration? Multiply it by 2. Okay, you would times this by 2, and that would be the molarity of your hydroxide. Okay, let's see. This was just kind of talking about neutralization reactions, where if you add an acid and a base together, you can get things neutralized. And so when acid rain falls, you can have situations where, depending on what the lake bottom is, you can have a granite lake bottom, or you can have a limestone, or like a marble, like what is marble? Like marble, like a calcium carbonate. And depending on what your lake bed is, it may neutralize. If it's something like granite, what do you guys know about granite? Why do they make countertops with granite? Because it doesn't what? It doesn't react. So if it's a granite lake bed, then the rain falls, and what happens? Nothing. It stays as acidic rain. But if the next lake right next door to it is made of like a limestone, then it will react and it will neutralize, and so that one can be less acidic than one that's right next to it. So that's like the whole idea of ocean acidification. Okay, so big thing, neutralization. Dilution, we think what? If it's a dilution, what's the equation? M1V1 equals M2V2. Don't forget, in a dilution, the substance you're starting with is the substance you're ending with. It is not changing. So if I have a 0.5 molar hydrochloric acid solution and I'm going to dilute it and make it a, 0.1 molar hydrochloric acid solution, they're both hydrochloric acid. That's M1V1 equals M2V2, okay? This is different because what does the A stand for? The acid. What does the B stand for? The base, okay? But the idea of the equation is exactly the same. When you dilute something, what's the only thing that you're changing? You're just adding what to it? You're adding water to it, okay? You're not actually changing the stuff that's in there, okay? When you neutralize, what we're basically saying is, what is it going to take to make my moles of acid equal to my moles of base? So what I want to make sure you do not forget is, what are the units of molarity? Moles per liter. And the units that we are supposed to use for the volume would be liters. And so this would be for my acid, and then you're going to do the same thing for your base. And what happens is your liters cancel out, and this is the whole idea of a neutralization reaction and using MAVA equals Mervet, is that our moles of acid would equal our moles of base. And then you know, okay, it's neutralized. Don't forget, neutralized does not mean neutral. If it's neutral, the pH is what, everybody? 7. If it's neutralized, your pH does not have to equal 7. Okay? It just means that the moles of acid are equal to the moles of base, and we're going to be talking about that in this second part of the unit. Okay, so what happens in a titration? We try to neutralize an acid with a base or a base with an acid. Typically, I always say that the base goes in the burette and the base, bases are usually blue when you do indicators, when you use indicators. So I always say it's like a triple B, okay? So base usually goes in the burette and bases usually turn blue. Okay, what is the end point? When the indicator changes colors. Perfect. What's the equivalence point? I like it. The moles of acid equal moles of base. Everybody, again, what's the end point? When the indicator changes colors. What's the equivalence point? Moles of acid equal moles of base. Awesome. Very good. Okay. Okay, so these are neutralization reactions, and so they're just double dating reactions. The only thing I want you to make sure that you do is you change your H2O to HOH so that it makes it easier to balance. So they're just easy double dating. So the H is now with the OH and the K is now with the NO3. Please make sure you rebalance your equations. What always goes first, positive or negative? Positive first. So if you have a metal, for example, that should always be written in the first position. Okay, what we were doing down here is we were labeling them so that we could set up our MAVA equals Mervet. So just making sure, if it starts with H, everybody, acid or base? Acid. What about letter D, acid or base? Acid, HNO3, LiOH, base, NaOH, base, and H2S, acid. That's half the game, right? Is making sure you know if it's an acid or a base. Then, obviously, if it's molarity, it's an M. If it's milliliters or liters, it's volume. So once you know those, then you can set up your equation. All right. This question was not asking us to solve for MAVA or Mervet. What it's asking us is it neutralized? Which means, what are they actually asking us? Are your moles equal to each other? Okay? And so what you do is you simply just set up MAVA and Mervet, and you check to see, are they equal to each other? And as it turned out, they were in this case. Okay? Right. So then we have a titration problem where, oh, they're just asking us for MBs, like what did it take to neutralize it? Same thing here, what did it take to neutralize it? I want to get to one where they're asking us for, okay, so if they give you any abouts, do not use abouts in a calculation, okay? So instead, and it says the base is supposed to have a concentration of 0.2. I can't use that either. Supposed to have, you cannot use, okay? So it says you place 1.5 grams of a known acid, and it's 147.5 grams per mole in, and then it says the solution's neutralized when you dropped 21.52 milliliters of the base in. What's the actual concentration of the base? Okay, so we know we're looking for MB. Okay, we know we're looking for MB. What can you tell me if it's neutralized? What two things have to be equal if it's neutralized? Moles of acid have to equal moles of base, which means if I can figure out the moles of one of them, I automatically know the moles of another one. So if they give me the grams and they give me the molar mass, what can I do? How do I find moles? All I'm going to do is simply do grams divided by the grams per mole, and then I get my moles, which means I know my moles of my base, and so then since I know how many milliliters of base it took to neutralize it, simply just divide it, and that's going to give me my molarity. Okay, so sometimes it's not as straightforward as it seems like it's going to be, and this is a similar type of problem again, but this was like the acids. So you, again, in this one, they said that we had 1.56 grams of the acid. Oh, we were looking for the molecular weight in this one. Okay, so we know the grams. Remember, everybody put your arms out. If you're looking for the molecular weight and you don't know, it's an unknown substance, what do? Grams, moles, grams over moles. And if you're looking for the molarity of something and you don't know what the substance is, everybody, moles, liters, moles over liters. Awesome. Okay, so depending on what you're looking for, you can also use that. So in this one, we knew the grams, we didn't know the moles, so we could find the moles using MB times VB, and then once you know that, you can plug that in to get your answer. Okay. All right. So what if you have an unequal ratio of H plus to OH minus? You're supposed to do solution stoichiometry, okay? It takes long. So what I told you was, I gave you a shortcut. So let me just clear my annotations. I'll come right back to it in just a second. So let's see if you remember how to do this, okay? So in this case, I have HCl reacting with calcium hydroxide, okay? So what I said to do was, set up your MAVA equals Mervet. But this one, my Ma is HCl, and my Vib is CaOH2. Does anybody remember what we do? How many H's are on this side? 1. So this side is times 1. How many hydroxides are on this side? 2. So guess what we do? Times 2. And then you work out your algebra as usual. Okay? You plug in everything that you know, and you'll be left with one thing, and then that's how you're going to solve for it. Okay? So pretty easy. Do not, if you're doing it this way, do not do a balanced equation. Do not do stoichiometry. You're literally going to use this in order to do that, and they will accept this, as long as you're clear on what you did. Okay? If it's a 1-to-1 ratio, obviously everything is just the same anyway. Just go back to what it looked like before. There we go. Okay. All right. Okay. And I think this is one of the last things for this part. Finding the pH at a random point in a titration. Okay. So we're only going to be doing strong acid, strong base. If it's a weak acid, weak base, you're going to make predictions, and that's going to be part of this next unit, the second part of the unit. But this we've already done, okay? So if you have a strong acid and a strong base, and you react equal volume, equal molarity, what do you expect your pH to be? 7, okay? But if, now look at this, because, so these were exactly 100 mils of a 0.3, 100 mils of a 0.3, you're going to get a pH of 7, okay? There's nothing extra. Everything's going to react. It's going to completely neutralize, and you're good to go, okay? All right. So now I want you to actually let me clear and it's do we want to clear annotations? Okay. I actually want you to see this. So, and by the way, if you have 49 milliliters of one, if they're the same concentration, strong acid, strong base, and 50 mils of another one, I'm going to show you in this part of the unit, your pH is not 7, and it may not even be anywhere close to 7. Okay? Your pH might be like 13, or your pH might be 2. Okay? The idea with the titration is that when you look at a titration curve, let's say I'm starting with an acid. Anybody want to tell me, typically what we have is we have pH going on this side. Where should my curve start? Down on the bottom or high up if I have a strong acid to start? Down on the bottom. I'm going to have a low pH. If I'm starting with an acid, I'm at a low pH, okay? So if I'm starting with an acid in my Erlenmeyer flask, that's what I'm testing the pH of. And then what I'm going to start to do is I'm going to start to add base to it, okay? Typically what's going to happen is you're going to get a line that's going to look like this, and then what? It's going to shoot up like this, and then it's going to curve like that, okay? This right here is what we're going to call the equivalence point. It literally shoots up in under 1 milliliter. And so when you do a titration, I'm trying to remember if we did a titration earlier in the year. You remember when it turns, it's like, it's not pink, it's not pink, it's not pink, and then what happens? All of a sudden you're like, it's pink, right? And it happens within like sometimes a quarter of a milliliter, okay? So if you miss it, or like a drop even. So if you miss it, you miss that like that straight line where the equivalence point is, okay? So if you're even a little bit under or a little bit over, you're not at the equivalence point, okay? So so what this says is you have 150 mils of a 0.3 molar and 100 mils of a 0.2 molar. What's your pH? Where are we? Okay? Where are we in this? And it's a strong base and a strong where's my acid? Oh, HNO3. It's a strong base and a strong acid. And they're a 1-to-1 ratio. Okay? So I do this as 4 steps. And I am going to want you to show it as 4 steps in the homework. Okay? The first thing I do is I set up a MAVI equals Mervet and I figure out my moles of each one. That's the first thing I do. Okay? Check to see, are my moles equal? What's going on with my moles? So I see that they're not equal to each other. Step 2, what do? We find the difference. We subtract. What are we trying to find? The excess moles. Which one do we have extra of? Which one didn't react? Okay? Because remember, it's like limiting reagents, right? So the one that you have less of is going to completely react with the one that you have more of. Okay? So in this case, we had less acid. So I subtracted the acid. I shouldn't have any more acid in there. Okay? And then my base, I have 0.025 moles of the base. But in order to figure out the pH, or the POH in this case, when you negative log, are you negative logging moles? What are you negative logging? Molarity. So we need the new molarity. And what's molarity, everybody? Moles divided by liters. But liters what? Liters of the entire solution. And if we've mixed these together, your liters is the total volume. So it's 150 plus 100, okay? So if I add those together, I'm going to get 250 mils, which is 0.250 liters. If you're finding molarity, you do have to be in liters, okay? It's not canceling out. You need to make sure you're in liters. So now I figured out what my molarity was. So all I'm going to do is negative log it, but that's my POH. So how do I get pH once I negative log it? 14 minus that, and that's going to give me my pH. So step 1. MAVI equals Mervet. Figure out your moles of each one. Step 2, what do? Subtract. It's that easy. Okay, so we're going to repeat this. Step 1 again was what? MAVI equals Mervet to find moles. Step 2, subtract. Good. Step 2 is subtract. Step 3, divide by the new total volume. Divide by the total volume because what are you trying to find? Molarity. Now that you have molarity, step 4, negative log it because that's going to give you pH or POH, depending. Okay, so those are your 4 steps. One more time. Step 1, MAVI equals Mervet, find your moles. And people will say, do I have to be in liters for this? If you want moles, you must be in liters. Okay, because otherwise you're not going to get your units right. So yes, in this one you do have to be in liters for that part. They're not canceling out. Okay, so you do have to be in moles for that. Step 2, so step 1, Mervet equals dividend, find your moles. Step 2, subtract, find your excess. Step 3, divide by the new total volume. And step 4, negative log to find your pH. Awesome, very good. Okay, this is, okay. So, if it's a strong acid, and they give you they want the pH and they give you the concentration, negative log it. Easy, okay? But then what we started talking about was, and yes, we did this in Unit 1, which I'm so surprised that, like, going back to this, I'm like, wow, we did this back at the beginning of the year. So, if it's not a strong acid, if it's a weak acid, okay, things are a little bit, or a weak base, things are a little bit different. What we need to do is we need to calculate K. So first, or they might give you K, okay, they give you the K, and then they're going to ask you to figure out what the pH is, or the other way around. They give you the pH, and then they say, what's the concentration of one of them, okay? So what we know is, we know that K is the same exact K we've been using in equilibrium, which is equal to products over reactants, okay? In order to figure out K, we need to write our expression, right? So we're going to write our equation. So in this case, for example, it's this, anybody remember what this thing is called? What is the whole ClO, Cl, what are all those called? Chloride, chlorate, perchlorate. What's this one? Hypochlorite. Everybody say it. That's hypochlorite. So what's the name of this acid then? Hypochlorous acid. That's hypochlorous acid. Okay. The acids are not going to be solids or liquids, like water's a liquid, for example. And remember, all the ionic ones we would say are solids when they break up and then they form their ions. Acids are actually aqueous. Do we include aqueous in equilibrium expressions? Yes, we do. What do we not include in equilibrium expressions? Solids and liquids, okay? But aqueous and gas are both included. So what we're going to do is, in this problem, it says, calculate the pH of a weak acid. This is literally the problem. Let's scroll down a little bit more. This is all the problem would say. And it looks just like the problem above. It looks exactly the same, except they give you a Ka. It looks exactly the same. The only difference is now they're giving us a Ka. And if they're giving you a Ka, that probably means what? It's a weak acid. Okay? If they give you a Kb, then it's probably a weak base. Not probably. It is a weak base. Okay? So if they give you a Ka, it's a weak acid. So all of this information is just extra stuff, but I want to talk about percent ionization, and I think that's the last thing that we had in this unit. Okay. All right, so what you're going to do is you're going to first write your expression, but in order to write the expression, we need our equation. Okay. We start off with 0.1 of the HClO. How much of it is going to break off? Well, they don't tell us how much of it is going to break off, so what do we call it? X. And if we call this X, it's a 1-to-1 ratio, that must be X. And so this isn't actually 0.1. It's 0.1 minus X. What are we probably going to assume about X? You guys remember? What do we probably assume? It's really small. Probably negligible. But in this part, they asked us, there are going to be questions, which there is one in the packet too, that's going to ask you to calculate the percent ionization. If it's less than 5% ionization, you can ignore X. If X is bigger than 5%, you actually are supposed to go back and do the algebra using X. Okay? So you do it first, and you calculate your percent ionization. If it happens to be small, then you can just ignore it. Okay? So let's kind of take this step by step. What do we do first? Write your equation so you can write your expression. I always say write the expression first, and then you're like, oh, I don't know the equation. Go back and write the equation. Okay? So then I plug in. They told me that my K was 3.5 times 10 to the negative 8 up there. It's equal to X squared divided by 0.100 minus X. I'm going to ignore X and just call it 0.100. So now 3.5 times 10 to the negative 9 is equal to X squared. And so then I square root to find my X, and that ends up being my H plus. Why is that H plus? Because what was the substance? Hypochlorous acid, the formula is HClO. And so there's only one H in there, and I'm calling that X, and X is equal to my H plus. So if I want the pH, all you have to do is negative log it, and that gives you the pH, okay? So then what they'll do is they'll say, do this, figure out the answer, and then they'll say, calculate the percent ionization. It might be like a letter D in the problem in an FRQ, okay? So we have to calculate the percent ionization. All percent ionization is what's your X divided by your original concentration, okay? Times 100. It's that easy. People always say like, oh my gosh, I'm so confused. How do I figure out the percent ionization? It's that easy. It's X divided by your original times 100, okay? So I did 5.9 times 10 to the negative 5 divided by 0.1 times 100, and I got 0.059%. So make sure you do multiply by 100. And when you do that, it's less than 5%. Do we have to include it? Nope, we're done. Okay. Again, if it was higher than 5%, what you would have to do is you'd have to do the foiling, okay, and figure out X that way. But then it's like, yeah, it's more math. They're not going to give you a problem like that, okay? But they will ask you to calculate percent ionization. Okay. We already know what acids and bases are. Oh, there's one more part. Conjugate acid, conjugate base. Okay. So these are Lewis acid base. They got rid of Lewis acid base on the AP, but you guys remember what Lewis did? Lewis was what guy? The dot diagram guy. Lewis is the dot diagram guy, okay? And so we know it has something to do with electron dots and pairs of electrons, okay? Does anybody remember? And I always like to do, it doesn't really matter, but I always like to do the acid because it starts with an AC. We said that the Lewis acid does what? Accepts the electron pair, and the base is the electron pair donor. Okay, so acceptor, acid, AC, they both start with an AC, and then a BD, but I don't know if there's a way of remembering that. Okay, so that was it for that. And so you can see here where this base has an extra pair of electrons here, and it's going to donate. And so when they come together, it's actually donating the pair to the two of them. And so now they're coming together, and that will be called like a Lewis acid-base pair. Again, they got rid of it. So, okay. What does it mean to be amphoteric? It can act as an acid or a base. Somebody give me something that's amphoteric. Water. Okay. Water can either, if it loses a hydrogen, what is it acting as if it loses a hydrogen? An acid. Very good. If it loses a hydrogen, what does it become? Hydroxide. OH minus. Okay. If it gains a hydrogen, what does it become? Which would be acting like a base. Then it becomes hydronium. H3O plus. Very good. Okay. So water can do both. There are quite a few substances. A lot of times they're ions though. So like for example, they'll say H2PO4 minus is amphoteric. Okay. If it's acting as an acid, just go to a blank page here. And you do need to be able to do this. If it's acting like an acid, what does that mean? It's going to lose a hydrogen. What will it become? HPO4 2 minus. Very good. Okay. What if it's so that's if it's acting as an acid. What if it's acting as a base? What would it become? Yep, if it's acting as a base, it's going to be H3PO4. Does it have a charge? No. Okay, so then it wouldn't have a charge. It would just be H3PO4, and so it can act as an acid or base, and that's what they'll say is amphoteric. Okay. All right. Okay. So the way this works is you take a look at the other side to see what happened to it, unless they tell you, like in this case, they say, HNO3 is we know is an acid. Okay, it's going to act as an acid. So what's going to happen to it? It's going to become NO3 minus. What do you call what's left over from the acid after it loses its hydrogen? You call that the conjugate base. And then the rest of it would be the conjugate acid. Okay. So if you're starting with, if they tell you in this equation, like, well, let's look at this one. So this one's a base. So then what happens to a base? Bases accept a hydrogen. So what is this going to become? NH4 plus, and you would call that the conjugate acid. okay? If you were to flip the equation around, this is the acid. In other words, what happens to NH4 plus? It loses the hydrogen, and something that loses a hydrogen is called an acid. Okay? So, and then a base, OH minus, gains the hydrogen to become water, so that must be my conjugate base. Okay? So bases are always going to gain hydrogen, and acids are always going to lose hydrogen. So just keeping that in mind. And then I think that was it. So let me just double check. Strong. We're going to talk about strong and weak. This is just, actually, this is a good time to just kind of go over this because we did do this before. Stronger acids, their conjugates are usually going to be weak, and then the other way around. A strong base should have a weaker conjugate. Okay, so just keeping that in mind. Properties of acids and bases, we already talked about. Acids will corrode metals. They taste sour if you were to taste them. Properties of bases, they release hydroxides, they neutralize acids. They usually turn red litmus, they do turn red litmus blue, whereas acids turn it like pink usually or red. And then the last thing that we had talked about were polyprotics. And the way that polyprotics work, poly just means what? Many. And prots, or protic, is referring to the number of protons. So polyprotic just means it has more than one proton, like H2SO4, H3PO4, I don't know, H2CrO4, chromic acid, okay? So if it has more than one, we're going to call that polyprotic, okay? And the polyprotic acids, usually only the first hydrogen that comes off is going to be a lot more than the second hydrogen coming off. And that's going to be a lot more than the third hydrogen coming off. Bases don't do this. Bases, if I have calcium hydroxide, the hydroxides come off equally, okay? The calcium leaves, the hydroxide leaves, and the hydroxide leaves there. They happen all at once. The acids don't, okay? So when you go to figure out the pH, we don't have to do this. Years ago we had to, and it's a big calculation. It takes a long time to learn. It's in the book, but it takes a long time to figure it out. So what they did instead is they kind of got rid of all that math piece of it and just said, it's going to be somewhere between losing 1 and losing 2. Okay? So I usually will just say, calculate what it would be if you lost 1, calculate what it would be if you lost 2, and then it's somewhere in between for your pH. Okay, and last thing, everybody, we're going to do strong acids, strong bases, and then I think we are done with this. Yep, that's just explaining that, and then that's buffers. Okay. All right, here we go. Strong acids. Okay, ready? Everybody say it with me. I clobber, no 3-chlor-4-sulfur. Here we go. I clobber, no 3-chlor-4-sulfur. One more time. I clobber, no 3-chlor-4-sulfur. So, HI, HCl, HBr, that's I clobber, no 3-chlor-4-sulfur. The only polyprotic one is which one? H2SO4, sulfuric acid. How is it easy to remember? Well, NO3 is the highest you're going to get with nitrogen, and with the chlorate, the highest you're going to get is 4 oxygens. So it's pretty, and with sulfate, highest you're going to get is a 4 too. Okay? So it's pretty easy to remember if you're not sure. And strong bases, do you remember the strong bases? 1As and why? Just because, sir. Because, sir, or casurba. Okay? So again, if you have something like LiOH, KOH, NaOH, RbOH, any of the 1As, and then Ba, Ca, and Sr are going to be all what? OH2. Those are alkaline earth metals. So those are going to be 2s. These are all going to be 1s. Good? Okay, awesome. So let's take a break. We're going to pull out the packet and get ready to go with that. And that's it for just a quick review of what we already did. Happy day.